Okay, so we try to begin. So let's start. Um, this is the 2025 presentation of uh, nonlinear optimization. I'm Xiwen Liu, and the topic of my research is nonlinear optimization in thermal image segmentation, which is advanced boundary detection using gradient control radio probes. First is introduction. So in the thermal stress analysis experiments, a laser is often used to heat the target sample in order to observe the relationship between temperature of the sample surface over time and heating pattern. An infrared camera is usually used for observation, which is then captured and exposed as a frame image. In the process of post-processing, exported data is necessary to determine the area occupied by the target sample in the image. When target recorded image is analyzed, analyzed, sorry. So in order to distinguish between the sample area and the frame area, it's necessary to segment the resulting image. In this experiment, the sample and thermal insulation material um, frame closely combined so that the the combination of under the condition of laser heating, the part of frame subject to heat transfer in the contact area and direct laser irradiation, and temperature of the part is close to contact with the sample is relatively consistent with target sample. So in this study, a gradient control based radial probe segmentation algorithm is used to follow by the two-step process of nonlinear least sequence squares, circle fitting, and geometric parameters in the samples in the frame image were extracted to segments. So for method, the first one method is pre-segmentation. Firstly, the image was imported, and the imported 3-channel T file was converted into the grayscale map. And the stair-step method was used to preliminary selection, and the initial binary mask M was obtained by selecting the largest connected domain. So we can see that the picture here is like a grayscale, gray value picture that we have. And the first time we have um, the original mask boundary like this, and then we let the center of the mass of mask be C0, which is CX0, CY0 coordination, which obtained by selecting the initial mask boundary. So the first centroid CO is average to obtain the initial value of boundary coordinates. But since the mask boundary mainly contains the target region, the centroid still provides a reference of the subsequent calculation. Then we apply the radius direction probe method to based on gradient control. Although the position of centroid obtained by preliminary segmentation can provide the center of the sample, the boundary profile of the target area is still not accurate enough, right? That's because you can see that the edge between there's some error. They still capture the frame of the sample, but not the sample itself. So in order to improve the accuracy of boundary positioning along the outward direction of the centroid, the gray derivatives of the image that difference radiation and the different rate or then detected a different angle to find out the boundary. So the first we find the grayscale. The first we find the grayscale scale of different probe over the different probe. So for each angle theta, the gradient is calculated by the sampling the grayscale value along gray starting from R0, which is that start from the estimated center on this at this region. So on each ray, looking for the gradient minimum on each ray, you see the bright blue line over there. So we're seeking of the gradient minimum location as detected negative gradient peak, which is R theta 0 equal to R minimum RG R theta. So if there are no obviously negative peaks, so we can skip the direction to interpolate with the adjacent direction and convert to R star theta back to Christian coordinates, extract boundary points. And traversal is performed on each angle theta to obtain set of boundary points. In order to further improve the accuracy of boundary, we need to average and smoothing the matrix we have. So in the grayscale at uh, different different rates and at each angle. So we let the original matrix be x from x11 to x1n1. Why we use n? Because that the probe edge we fetched is different compared with others. Means that we use different radius. We have different radius at different angle, so that n is not the same around different probe. From x1 to x360 means that we have different angle of probes. We detect all the radius. Yes, that's it. Um, assuming that matrix is y after the average operation. The average operation as follows. For the We use the average of 3 points to make it smoothing, make it to smoothing the gray value of x. At average point like center point or edge point, we use 2 because we don't have other points to average it, obviously. Um, so the fourth step is nonlinear circle fitting. So as we have here, the first, the radial distance from the edge of the probe to the center of the preliminary estimated circle is calculated. The median of this distance is used as initial radius estimate of the fitted circle, and then the objective function is constructed. So there are two main parts of objective optimization function of f, c, x, cx, c1, and r. The first part is um, the fitting term, and the second part is penalty term, which penalize the duration of the center and radius of fitting circle from center to radius of the expected circle, respectively. So the function is typical nonlinear least squares problem, and is often solved by the method such as Gauss, Newton, or something like that of Liebenberg method. And there we use the needle-meet method, which is f-min search function in MATLAB. So needle-meet function simplex method is a derivative method based on geometry simplexes that doesn't rely on the gradient calculations, and which is suitable for small scale optimization problem like this. Okay. For such a method, we have a convergence theorem. When the function is continuous, smooth, and unimodal, such a method converges to a local minimum, but doesn't guarantee a global optimal solution, which is very reasonable. That because when we're trying to find uh, the edge of the boundary, we not always fetch the very end of the whole picture, right? We just need to find the local minimize local minimization local minimizer at the edge between the um, material and the frame itself. So from Jeffrey C, it makes that fr to r continuously differentiable and bounded below. So we let the algorithm produce a series of complex simplex with the verticals xk0 to xkn, and which is satisfying the assumption that, well, while satisfying the assumption that the objective function has strict convexity, the local limit converges to a stationary point. And it means that the delta f is equal to 0 and the diameter of simplex simplistically approaches to 0. Okay, so let's turn to the visual debugging and validation. So as you can see here, during the actual debugging of the code, we draw probes at 15-degree intervals and equal space. You can see here, there. It's like this, like a star. So we have it presents g theta r is equal to f theta prime r. it will satisfy the minimization of G theta r is smaller than negative tau, and tau is the very edge. Otherwise, the probe exceeds the initial mask's radius, and the mask itself needs to be selected boundary. And next, in order to visualize all the detected boundary points and be linked, we stitch together with global curves and write down radius at each angle. We have two theorems here for each shift continuously and theta f theta 0 to R max compactness, there at least one optimal solution. If there's only one point below is in the threshold, there's a unique optimal solution P theta G theta. If R star theta is log optimal of P theta and G theta differentiable, and then we can assume that mu is larger or equal to 0 of such an equation. Um, So if mu equal to 0, R star theta is smaller than negative tau. And if mu larger than 0, G theta R theta is equal to negative tau. And which is results. The diagram on right side reflects the radius selected at different angles. The FC, the F, the the um, the x-axis is the length of radius. The x-axis is the length of radius, and the range of the radius from initial mass to from 0 to the angle direction detection. And the ordinate is gray value. The y-axis is gray value also. The corrected value position is marked with a red circle on the gray value intensity curve, and specific method so is to sort the slope of each group of gray intensity and compare with the steepest slope dropped control variable. If the comparison results in steepest slope that exists control variable, the steepest point is taken the new edge of the selection point. Otherwise, original edge mask is selected to the selection point. You can see here and let's say there, right? So for the figure here, the image reflects the corresponding segmentation curve on the grayscale plot of the input image. Among them, the outermost yellow curve, as we see before, is dividing the line of the primary mask. We take center mask C0 as the center of the circle, and the mark is with the red plus sign. The probe is emitted outward from the center of the circle, represented by the light blue dotted line on the diagram. Just simply link it together. So the furthest point reached by the probe indicates by the bright green dot, and the expected edge is drawn with line connection between and two furthest point. For the results, we have segmentation curve, and here, yes, there. The figure here shows the final fitting mask boundary circle compared with the two calculated boundaries, and it can be seen that the center of the fitting boundary circle is offset from the initial prediction. It can be seen from here to there. All right, so let's turn to comparative analysis. So we compare it with the let's say the manual mask at below, and we have our auto mask at above. You see that it's very close to each other, and we have I just say collect each white pixels, the total amount of white pixels of the mask. I see above is 27,504, and next one is 27894, which is very close to each other. Um, the above figure is an analysis compared with manual segmentation here, where the inputs are segmentation mask and manual segmentation mask output by the automatic script are respectively, and two regions are superimposed on the difference map of comparison. So firstly, the two white regions are subtracted. Yes, so first we subtract such a region. How can I say? Uh, so the first we input the manual segmentation, and then we transfer to gray value picture, and we uh, I transfer it to a gray value picture, and I subtract each region from different output. Means that the auto segmentation and manual segmentation, and now we have the difference between. Uh, and then I save the difference to a how can I say, a RGB picture. So at the first channel, at the channel first, I save the last the least of mask one, which is automatic mask, and at the second channel, I save the manual mask. You see here, so we can make a comparison of uh, two different way of mask. So you can see that automatic segmentation accuracy is pretty much higher, it's, which significantly improved the compared with edge detection function edge built in the MATLAB. In the next page here. So here's the uh, here's the edge function from the MATLAB itself. So normally we just use it to fetch the binary mask. Um, so compare with the method I have, which is have better quality, of course. I think that's it. Let's see. Um, it's very short. How can I say? Um, differentiable solution. Yes, that's it. So before that, I think something is still under clarification. So we have a 2 kilowatts carbon dioxide laser, which is 1000 meltbeam. It will be generated and heat the scanner and above here. And we use a laser lens to generate a scanning pattern over the sample itself and heating the sample surface. And so by such ways we can um, generate a heating pattern by manually, not like a torch method like this. It cannot be specifically calculate. It's only can it somehow it can just generate a curve like this, so that we cannot control it very specifically. And by applying cooling condition, we place a substrate air jet nozzle um, to cooling the sample by blowing the cooling air. So we captured from two sides. One is from above side. One is like an infrared camera above. One is an infrared camera below. Um, the below camera is third infrared camera, 75 to 40 mega minimum meter, and which the detecting temperature range is 300 to 2000 Celsius. I think that's all I have. Is there something? Oh yes. So here's the reference. I think there's my last 25 minutes. I think still be good. 4 minutes left. Hmm. Oh, so the next step of the future of such a um, analysis is that the next step is we use a different shape of objection. For example, like a square shape or even more complex. Somehow we use like a fin shape. But now the detecting um, method can only apply for round shapes like this. So the next step is like to find out a better way to make an auto segmentation. All right, that's it. All right.